Well, good morning, E-Techians, and good afternoon to the afternoon E-Tech class. This is Mr. Kinney here with today's lecture. We are doing Ohm's Law water analogy. Hopefully this can kind of help you visualize what's happening with these circuits with something that's a little more familiar and kind of pretty. So let's move this over here, and let me get zoomed in a little bit. All right, so let's get this titled. Let's see, I'm going to use black for the title. Ohm's Law water, you can put H2O if you like, water analogy. Okay, and we will put, oh yeah, Ohm's Law, remember, the version of it I like is Vir. V equals IR, because for me then, whenever I have to solve for either current or resistance, it's easier to rearrange them that way. But you don't have to do that. So let's see here. Oh yeah, and this is voltage equals current times resistance. So first thing we're going to do is going to draw some waterfalls, because waterfalls are pretty. Later on we'll see some videos of some waterfalls. Now for this I think I need to change my blue pen. You may want to do that. Now we're going to draw, well, more or less, here's what the finished product will look like. You can see on my, okay, we're going to end up with something like this on there, okay, a whole bunch of waterfalls. So here we go. So off here, you're going to need a little bit of room to write some stuff over here. We are going to put voltage, okay, voltage in this analogy equals the height of the waterfall. Okay, current in this, so that's we have Ohm's law, that's V. Current, which is I. Okay, so current and will be in flow rate. Now for height we'll either use, well, I'll give you feet and I'll try to give you meters as well. Not feet per meters, that's like either or, sorry. Current, now we're going to use cubic feet per second. Sometimes that's abbreviated CFS, cubic foot per second, okay? So that's the flow rate. Cubic feet, I mean a cube about this big every second, pardon me. And V equals I times, and R in our analogy is, oh, let me zoom that in for you so you can see that a little bit more. Apologies for not having that too zoomed in there. There we go, focus, there we go. Now resistance in our analogy is gonna equal, this is resistance. Measure how hard the electrons have to move to go through. Resistance is going to equal rocks or obstructions. Rocks, obstructions. S-T-R-U. Rocks or obstructions in the river flow. All right, so first off, we're going to draw some diagrams here. Let me zoom back out now, because now we got the big picture. We're going to draw our 1, 2, 3, 4 waterfalls that I'm going to use to represent this. And here we go. So actually, for the first part, let me zoom out so we can see the whole page. Just that, because you think you need the whole page for this. So first off, we're going to put, I'll do this in black, a raindrop. Okay, so we're going to go like this all the way to the bottom of the page. We'll put our drop. Okay, now look at, when drops are falling, they really look like that, but we tend to make raindrops, or drops look the little, because that's what they look like when they're about to drop off something. Anyway, there is our raindrop. Raindrop. I guess I already labeled it at the top. Now, the next one we're going to do is, and we'll see an example of it in the video, Bridalveil Falls in Yosemite. We'll also see Yosemite Falls, but Yosemite Falls is really 2 falls, so we're going to do Bridalveil Fall. Now, bridal is, when they write it, Bridalveil is one word. Oh, let me go with my black pen. B-R-I-D-A-L, V-E-I-L. Bridalveil Fall. And that's in Yosemite. When I was looking up the numbers for this, it's like there's a whole lot of Bridalveil Falls in the world. Anyway, you don't care about that. Bridalveil Fall looks something like this, okay? So we're going to represent this coming down. And I think I represent it. We'll go about halfway to the page. These drawings aren't necessarily to scale. We'll just do a couple little lines here. Okay, maybe we'll do a third one, but on this third one, we're going to kind of get wispy and like that because Bridalveil Falls, it gets really wispy at the bottom. All right, the next one. All right, come on. What's the most famous falls you probably think of when you hear about it? Okay, I know a lot. It can be very romantic, apparently. That's going to be Niagara Falls. In the video, we're going to see a really beautiful fall in, like, I think it's Argentina, Chile. Oh my goodness, it's amazing. All right, now for Niagara Fall, let's draw it like this. Here's water coming here, then we're going to come down like this, and then we're going to go this way. Now we're going to repeat that pattern, slightly staggered, because now what we're doing. Okay, so let's draw. Okay, now this is, Niagara Falls is kind of. This is just a segment of Niagara Falls, okay, because it kind of goes around here, then it comes around over there, and you'll see that in some of the video clips. Video clips are fairly long. Okay, I think that's as much as we're going to get. Let's just put a few rocks there, okay, and then we'll have the river. Okay, there we go. And lastly, we are going to put a canal weir. Oh, I hope I spelled weir right. A weir, have you ever seen some of the canals in town? A lot of times you'll see there's like what looks like a little dam across them and then they fall over. So, canal weir. And you know what? I'm going to have to verify the spelling on that. I know it's kind of a weird name. Okay, so let me get back to my red here. Now, with the canal weirs, what you've got a gentle little fall. Not very much. Now, again, these are not to scale, okay? And let's see, we'll go maybe 3 like that. If you really want to, we could put here's the side of the canal over there. I'm not going to draw this side because it'll obscure us. Okay, so a canal, we're a little tiny one. And just so we know for reference, we can have a person standing over here as a reference point. And over here for Niagara Falls, we can have a person standing here on the observation deck for a reference point. And for Yosemite, for Bridalveil Falls, we can, let me zoom in so we can see those a little bit better. Okay. And then, of course, for Bridalveil Fall, you don't ever want to go up to top of Bridalveil Creek because you'll die, okay? And a raindrop, well, okay, it's like, okay, there we go. There's a scale. There's my hand for the scale there. All right, so voltage. I'm going to do voltage in a pleasant color. Voltage equals height. And this raindrop potentially can fall. I think I estimated, as a pilot, we used to go flying in the rain, and we'd be under altitude. Let's see. I think I was estimating that rainfall that was going to be about I want to get the right one here. I don't want to tell you wrong. I'm going between two notes, two sets of references here. Let's see, what did I decide on the, there we go. Yeah, because I had my numbers here. So we're going to say about 3,000 feet, okay? So height equals about 3,000 feet. Okay, now for you purists out there, that's about 914 meters. Now, this is going to represent our voltage, okay? So on this diagram, let me zoom out here. So when we're talking about voltage, this raindrop has an incredibly high voltage, okay? Very high potential for it to fall. And then now we're going to come over here and do Bridalveil Fall. Bridalveil Fall is its height, okay? Again, that's going to equal its voltage here, is 620 feet. 620 feet. And if you want to be metric, we'll do 188 meters, just for the pure of heart. And then we have Niagara Falls over here. And Niagara Falls is 167 feet. That would be 51 meters for you purists, okay, from here to the bottom. Okay, let me zoom in there some more because we need to get that, see that a little bit. All right, and then the canal weir over here, we're going to say that's about 3 feet. When I go for a walk, that's normally what I see, which is about 1 meter. Okay, so there we go. So what we have here in this water analogy, we have some very high voltage. Very high voltage. We have high voltage. We have medium to low voltage. And over here we have low voltage. And so there we go, low, because there's not much of a drop, low voltage. So there's a nice analogy for you. Now, we're going to get to current flow rate, okay? So now cubic feet per second. For this one, I'm going to go back to my blue pen here. Wait, I have a green one. I'm going to use green. So, in my research, I found out that, let's start over here with the canal weir. Let me see, where did I put my notes on that? Oh, I'm going to be mad. Oh, there we go. So, what these can be is, for the canal weir, it can be about, now of course it depends upon the size of the canal, but for, we're going to say about 900 cubic feet per second. Now that's going to be a fairly nice big one of the wider canals. Now for Niagara Falls, oh my gosh, 65,000 cubic feet per second. Now again, this is representing now current. Okay, so here we have with this canal, we have low voltage, but we got a fairly good current. That might be kind of like sticking your finger in a light bulb socket. Okay, here's Niagara Falls now. Now we've got moderate to high voltage, okay, and we've got, oh my gosh, look at the current on there. That is a lot. That's like, whoa, that'd be like, 1,000 amps or something like that if we were to use that. So let's see, so this would be, what do I want to put? I'm going to just put I here just so we remember that that is current. Oh, let me zoom in a little bit so we can see those numbers a little bit better. Now, Bridalveil Fall. Now, Bridalveil varies, but the average flow rate at Bridalveil Fall, when it's actually flowing, because it doesn't flow the air, but when it's flowing, it's average about 100 cubic foot per second. Okay? So, again, so what this represents, so over here at the canal, we've got fairly fast, we got kind of high voltage. Here we've got, moderate current, very high current, and really small current, believe it or not. And, okay, so now look at, I estimated, okay, now we're going to go over here. I estimated that, a raindrop is about 1 milliliter, and let's say a raindrop hits every second. Okay, well, I went and did some calculations on my iPhone. I got this really cool app. It's called Units. Oh, you should get it. Let me see here. Let me put it here. UNITS. Okay, Units. Come on, there we go. And when you put it in there, see, there we go. I put in, well, I had to first figure out, okay, you don't care the calculations that I had to end up doing. You can't see it because of the angle on there. But come on, there we go. So you can put in different stuff. Like right now you can see there's, okay, you don't really care about that otherwise. But, so, oh yeah, I figured out that a cubic foot is 0.037 cubic yards, and then that told me how many milliliters. Okay, so anyway, maybe you're not into calculations like I am. Here, the point of all that is that the current in cubic foot per second I estimated to be 0.0, okay, 4 zeros after the decimal point, 0.0036. cubic foot per second. Wow! I mean, wow, that is a really tiny amperage. That might be like the amount of amps that's going to the little glowing light that you see on the sides of the room by the light sockets, okay? Okay, not a lot of current. Doesn't take a lot. All right, so now, so the last part of this is going to be resistance here. So resistance is going to represent the obstacles that the object meets, okay? So while this drop is falling, okay, while it's falling, and in general at all, when any of these waterfalls are falling, okay, now this is going to be resistance. Oh, I better do this. I'm going to do this in black, because you know what the old Star Trek saying is, resistance is futile. Okay, that's, okay. Resistance equals the amount of obstructions. / rocks. Okay, we already wrote that elsewhere, but just a reminder. So, while these are falling, while any of these waterfalls are falling, very low resistance. Okay, very low resistance. Now, we can almost say there is no resistance. Of course, now that's assuming that there is no air, or that what's falling off here isn't a water drop. It's a spherical chicken in a vacuum. But it's not. It's a water drop. So while it's falling, resistance is zero, almost zero. But then when you hit down here at the bottom, the raindrop, boom, major. Resistance here is. Oh, it's approaching. Oh, I can't remember the math term for it because I'm not a math. It's approaching. Really low. Okay, resistance is low while it's falling. Oh, I got to get the right math terminology. Mr. Lake will help me. Over here, resistance goes almost to infinite. Boom, almost. Okay, I know there's a math integral or differential or something. Okay, I've got to learn that. Anyway, resistance goes really high up. Over here, okay, low resistance while it's falling. low resistance while falling. Then when it hits down here, we're going to get high resistance. So it's almost like, if you imagine this as a circuit, this is just a nice big wire. And then right here, you've got a, oh, I'll draw this in a pencil. It's like, don't draw this in, okay? Wait, I can't find a pencil. Okay, wait a minute, this is, okay. It's like you've got a big, giant, 2,000 ohm resistor sitting on the edge of here, okay? But then it does flow out. Eraser, okay, now I lost my eraser here. So in circuits, resistors look like, okay, you don't care about that. So now let's talk about after they hit. So obviously hopefully you got the idea. Very low resistance while they're falling. Now they hit the ground, they hit a great big resistor down here. Now they start to flow. Now, need black here for resistance. So what I'm going to do is let's do Bridalveil here. So at Bridalveil, when it falls, and you'll see pictures in the movie of people sitting on some rocks by Bridalveil Fall. Okay, so it hits the big resistance, but then the river begins to flow. Okay, now let's draw this kind of weird jaggedy because there's rocks everywhere at the bottom of Bridalveil Falls. Now, and they're slippery too. I take this from me. There's a really pretty little pool underneath here that when I was a young man in college, I went and swam in that while the water was falling, not realizing if one little rock falls down. Anyway, so now, right here, this is high resistance. Okay, resistance is high right there. But then after a while, that creek gets away from those rocks and it's just kind of flowing towards a meadow like that. So now we've got low resistance. Okay, the water flows picking up a little bit like that. And then what can happen is, okay, so that's the end of our analogy there. But we got where there's rocks, obstructions, it slows it down. Oh, hey, maybe you get down a little bit further and somebody has put in, we'll draw a partial, what looks kind of like a Ferris wheel here. Maybe somebody's got a little power generating plant. They've got a little water wheel kind of a thing, like you see in the back of paddle boats. Okay, this will increase the resistance. Okay, so now resistance is going to be a little higher. Okay, resistance is increasing if you have, a little, a power station. So over here, back to Niagara Falls. Okay, Niagara Falls, the water flows when you see it. It's fairly, we get a little bit of resistance here. Okay, so we have high resistance when it hits. Okay, low resistance from these rocks in there. Oh, zoom in, you can't see that. Then as you flow down the hill a little bit, okay, you go down, and then you're going to get into an area where, okay, let's say now we start getting more rocks. You get more rapids and stuff like that. Usually, though, wherever there's rapids, it's because you have a geologic land formation. You've got soft rocks meeting where there's hard rocks, and the soft rocks erode quickly, leaving the hard rocks on top, making it fall. But this isn't geology, but geology is the reason that we have physics and chemistry, because it really ties them together well. So right here you can have, and what tends to happen is the river flow spreads around, has to get around these, but then, so we got high resistance, and then the river can come back together, and then there's some places you may get a spot, maybe it goes through a little valley, okay, and the water narrows, it's going really fast, it's got really high current, it may be going at 100,000 cubic foot per second depending, but there's low resistance. Now let's think about this for a moment, about voltage equals I times R. I'm going to do some analogies here. So let's talk about current and resistance over here. Let's assume we're going to keep the voltage the same, which is the height of the waterfall staying the same. That's not going to change here for us. So we've got current and resistance. Okay, what happens if we, like from here to here, we have increased the resistance? Now I like using numbers for this. Let's say the voltage is 1. Let's say the current is 1, and that the resistance is 1. Okay, 1 times 1 equals 1. So that would be what's happening right over here. Okay, but now we come over to this part over here. So let's rewrite V equals IR. Now we're going to keep voltage the same. The waterfall hasn't changed its height, but we've drastically increased the resistance. Let's say the resistance has doubled from all these rocks. 2 times what equals 1? What does the current have to do if we don't have any change in the voltage? Okay, we're making resistance higher. What happens to the current? Okay, let you think, okay, so 2 times what is 1? Okay, you're talking to the person next to you. Okay, well, you got to multiply it by the inverse of the number to find out for that. That's right. This becomes, the current becomes 0.5, or 1/2. So now the current, let me rewrite this. So current equals 0.5 now, excuse me, voltage equals 0.5 times 2, because we want to keep voltage at 1. And 0.5 times 2 still equals what we started with over here. So if we say that that resistance and current are inversely related to each other. If you increase one, increase the resistance, you're going to decrease the current. All right? So we're going to be talking a little bit about those analogies of increasing one, how it'll change the other. So I'm going to stop this water analogy now. Hopefully, because for years I used to wonder, how could a raindrop fall from miles high, hit me on the head, and no big deal? Okay, but then if I'm sitting playing in the dry canal bed behind my house, playing with my army trucks and my astronaut toy, I'm doing stuff down there, and all of a sudden they turn on the water flow, and this isn't very high, but all of a sudden I'm being hit by 800 cubic foot per second. It's like, whoa, this isn't very high. This water's not falling very far, but man, I'm like in trouble. I'm like, I'm tumbling. All right, that's it. Thank you, and have a good day. We're going to continue on with class words. So long.